Okay, good morning. Hope you made it well, had a nice dinner yesterday. As I've already said, so yesterday we looked into streaming I/O. I hope we might have fixed some of the permission issues with the Jupyter Notebook by now, because we are going to use the Jupyter Notebook for the first interactive session today now again. As I said, we are first now going to look at some actual data sets produced, in this case by Pick on GPU. You see here a list of some scientific simulations implemented or that implement OpenPMD output. This is not a comprehensive list, so there is a list of projects on our GitHub site, which is also worth looking into for finding out about tooling that you can use with OpenPMD, which we are going to use, for example, now to visualize OpenPMD data produced, in this case by Pick on GPU. These are some other simulations using OpenPMD. But like I said, we're now more interested in analysis visualization workflows. So up here you see the OpenPMD viewer, which we are going to use first. This is a library developed on top of Matplotlib. And the idea is, given that OpenPMD already defines the physical metadata, that means the files tell us what is actually in there, so we don't need to put in things like plot titles, axis labels, or scaling of the axes manually, but the OpenPMD file knows roughly how it wishes to be visualized, and so the OpenPMD viewer does all that stuff which you would do by hand in Matplotlib automatically. And you can use it either as an API or with a much more user-friendly interface that provides you with a little GUI in Jupyter, which we are going to use for exploring a Pick on GPU dataset. Other options you see listed down here. So ParaView is the next thing that we are going to have a look at. The YT project visits are also have connections to OpenPMD. And for other data analysis tasks, we have stuff like Dask, Pandas, and Rapids. And all of this is not rocket science, really. It's really providing an adapter for OpenPMD data to these code bases and providing examples and documentation. So basically, the way that computer science should work, not by implementing everything anew, but by having modularity from one code to the other, so you can have an integrated workflow. So for the first part, we are going to switch over again to Jupyter Notebook. And we found out by now that you need to put a little source command in front of the environment specification, so we're going to do that. And we just tried it out with René's account. It seems to work what we are going to do today with an account that is not mine. So hopefully it's not only René, but most of you will be able to launch it. Let's try. So let's head back over again to lumi.csc.fi. I don't want to store my password. And create a Jupyter session. Again, bare Jupyter, not Jupyter for courses. We pick the reservation for the last day. And now the important bit, please use 16 gigabyte of memory at least, or please use 16 gigabyte of memory so that we don't overburden the allocation. About 16 should be fine for everyone. And 4 hours should be fine. Now this is what I told you to type yesterday. please add this little thing in front, because for some reason maybe I just set the permissions wrong, but you seem to not have executable rights, and you can fix it by typing that little source thing in front. Otherwise, I mean, we can get some more CPUs, doesn't matter so much. And launch. So this is now starting, and again it will take a little while. Let's see if that works. Oh, come on. Why did it work for you and not for me now?
Do you edit the source?
Yeah.
So for me it worked with an outsource before.
Okay. So please look into that output.log. If you get an error about Python not being found, then cancel this again, and we will try again without adding that source command.
Oh, was there a space in between?
Yeah.
The source? Okay.
We'll try. So.
It's Schrödinger's notebook.
Yeah, something. Let me just try it once more. Launching a second one, and this time again with source. I'm making sure there's... So if this one opened from earlier, I can cancel it. No, the one where I use source doesn't work. So for me, it works without the source command. For you too?
Yeah, without source.
Okay. Fine then. Forget everything that I said about using source.
Yeah, the chat also said.
Okay. Apparently, my attempt to fix the permissions actually worked. Now we're going to close all of that and head over to day 3. Yeah. Exercise 14, and there is an OpenPMD viewer notebook prepared with some instructions. And the basic notebook that you get here is also what you get when installing the OpenPMD viewer on your system, and you can just, there will be a binary command that you can launch called openpmd_notebook, this one, and it will pre-fill this notebook that we're just looking at with this information, with the information necessary to start a basic GUI for the data that you want to visualize. I already added the path into the data that we are going to use. One little difference that you will notice compared to the OpenPMD API, this does not specify the data itself, but the folder that contains the data. That is for historical reasons, because the OpenPMD viewer was written when the OpenPMD API was not yet. So they just do it that way and then try to figure out what is in that folder. So let's just start this thing and let it run through. And ideally, you see this GUI now launching. The first thing that I will ask you to do here for the particle side of things, the particles generally take some time to load. So in order to have the interface be a bit more responsive, unselect this always refresh button here. And in order to make the GUI start doing anything at all, we just need to select some other field type. Let's, for example, click at E, the E field, and we will see a two-dimensional slice. As I said, the OpenPMD viewer is a two-dimensional visualization based on Matplotlib, so you need to select a slice. There are 4 meshes that you see here, and this pick on GPU ID provider, please ignore that. That is internal information that has no use visualizing. What we see again is here for B and E, these are both vector fields, so we can select between X, Y, and Z components. For charge and energy density, this is not possible. So up here we can select an iteration, so we are currently at the start of the simulation. We can jump forward, or we're not directly at the start, we are at step 1000, and see the simulation progressing. Down here you can select a slice and select where the slice is at. So maybe I will give you a minute or two to play around with this interface a bit, hoping you were mostly able to launch it. And maybe to figure out the direction into which the simulation and the laser pulse is progressing. So maybe someone can give me an answer on that. So is it X, Y, or Z? I think you know it without looking at the data, right? Yeah. Anyone got an idea?
Plus Y.
Plus Y was the answer from the auditory, so let's try it out. Currently we're looking at a slice through the plane Y, so we don't really see the direction where the simulation is progressing, because if it's really plus Y, we're looking directly at the laser. So let's pick another slice, for example Z, and maybe let's go a bit out from the middle to see a bit better the effects of the laser pulse. And we actually see, okay, that seems to go in direction of Y. Maybe let's go a bit back in time. And maybe I will try to make this a bit smaller so I can have everything on. Does it work? Yeah, that works. Yeah, let's go back in time. Let's go forward in time, and it seems correct. The stimulation is progressing in plus Y direction. So now let's visualize some particles, and the way that that works in the OpenPMD viewer is it plots particle histograms. So let's try this first. So we have here particle quantities to visualize. Particle quantities, again, their quantity along the X direction or the Y direction, for example. So what we are going to do is select the Y-axis here. Click refresh now. And this is trying to connect to my kernel. Is it possible that I forgot specifying the memory? Wait a minute. Might be that I need to restart my Jupyter notebook. Yeah, it actually crashed. Okay, I'll quickly restart the notebook. So that's why I asked you to specify the memory. Not memory file. Yeah. So generally, the particle data is often the heavyweight data that needs more disk space and generally infers the more compute demands. So trying to visualize the particles now was what actually made me realize that I had misconfigured my Jupyter notebook. But of course, I only did that to give you more time. Let's select something again. There we are, particle selection. I unselect, always refresh. We want to plot the histogram for the y-axis and try this again. So up here we see that the kernel is busy. Now it has computed the histogram. This is a 2D histogram that seems to roughly fit the data that we see up here. We can also plot 3D histograms, so let's plot a histogram that actually fits the plot that we see up here, so y and z. And there we go.
Is it normal that I don't see the first image?
Can you try going into the field type and selecting some other field there? Not the...
Not B, but something else?
Just something else, yeah?
The evil charge density.
Yes. Now you can also go back to B and it should visualize that. It just needs some initial interaction, otherwise it doesn't do anything.
Okay.
Now, just quickly... Yeah. I'd rather give you one more minute to play around with things and then I'll continue with compressing that dataset that we just saw. Okay, then let me go on with compression. Because the data set that we're just visualizing was written without any compression, before talking about compression, I need to talk a bit about how data is organized on disk in HDF5 and ADOS, because they use very different approaches. HDF5 generally uses a very structured approach to output data in the simplest case. So if you just use the C interface for HDF5, don't configure anything, but use really the simplest calls that write any data at all, you will just write an n-dimensional array to disk as really just that, as a contiguous buffer. So it will be on disk like that, which is simple enough, but gives you some trouble when reading back from file, because you might want to read along the x-axis, then everything's fine because the buffer is contiguous. But if you want to read a chunk like that, this will make you read much more data than you would want to read. So what you would normally do in HDF5 and what is necessary for basically all advanced features of HDF5, including compression, is that you would specify a chunking by specifying a regular size that data sets are subdivided into. And this would then look like something on the left-hand side, that you have a chunk data set on disk. Every little chunk is for itself contiguous, but overall it's organized as a list or map of chunks. So if you read something like this, then the overhead that you will get is defined by the size of the chunks. So generally, it's not trivial to get a good chunk, or to know what a good chunk size would be. Depends also a bit on your read patterns. Depends on the dataset size. In OpenPMD, we have a heuristic implemented that figures out a chunk size automatically, but you can also set it explicitly if you want to. On the other hand, ADOS makes it very simpler on itself by using a log-based or log-formatted output, meaning as in logbook of operations that came, not as in logarithm. So don't confuse that. That's the confusion that I had, at least when first hearing about that. That means that operations are written onto disk in basically just the way that write calls are presented to the library. So, for example, imagine we have a 2-node data producer running with 4 ranks, so 2 MPI ranks on each node. We have this blue little things is supposed to represent the subspace computed by each rank. And the green boxes represent the actual data chunks written. So we have a data producer that for some reason decides to produce sparse data. And this is really what you will get on disk also. You will see the single blocks of data. If you write data in a very convoluted way, then also your output will be very convoluted. If you write data in a more structured way, for us in PickOnGPU, that's the case. PickOnGPU has a very structured output. So for us, the HDF5 way of doing it would be an unnecessary overhead, because it would basically help us force a situation that we have already. So for us, this is the more performant thing. But generally, especially the read performance will depend heavily on the write patterns. That's also where I quickly mentioned yesterday, going back to some other slide, to this slide down here. That paper is on online data layout reorganization for for defragmenting internal data structures, and finally also defragmenting output for better read performance. which can happen, for example, if you have a code that heavily load balances or has or heavily relies on mesh refinement. But actually, for mesh refinement, also HD5 is sometimes a bit difficult because naturally the support for sparse datasets, as you will get with mesh refinement, is better in a format that doesn't care about if the blocks that you write are covering the full region or are even overlapping each other, which ADOS does not. So two very different approaches. And compression will then operate on these blocks or chunks. Now the question about compression, this is a research that Axel Hübel did some while ago already, so 2017 that is. The question is, how does compression affect our performance? So one thing that I already mentioned is we have the situation that our code is GPU only. We have free CPU resources, so why not use it for compression anyway? But also, you can imagine compression takes time, but it also reduces your data size. So maybe if you have a fast compressor that still manages a good fraction for compression, it might actually be possible to make the cut that the overall performance will get better. And it is possible, but difficult to reach, and you need to do things correctly, and things will, again, not be very predictable, but you need to test them out. So here are also two different systems, and things behave different on both systems. So you can make the cut, but you might not. Let's try this out. Heading back into the Jupyter Notebook. I will copy the path for the OpenPMD dataset and create a new terminal up here. And let's maybe first try looking into the blocks. As I said, ADOS writes the datasets per blocks. So let's look at the blocks that were written by ADOS. In this case, by specifying the flag minus uppercase D for decomposition. And we'll just look at step 1000. And we see this dataset was created by 6 GPUs apparently. No, 8. 8 GPUs.
Where's the data?
You can copy the path from this. So we are now using that dataset. I'm a bit confused actually why some of those wrote 6 blocks and why some of those wrote 8 blocks, but that's nothing that we should care about right at this moment, because that's a thing about Pick on GPU that I need to look at. But anyway, we see the data blocks. And these are uncompressed, so let's look at the file size of the dataset. That's 5.8 gigabyte. I have prepared inside the folder that we're in a configuration for compression that again uses BLOSK at the highest compression level. And we are going to use a tool that is called OpenPMD Pipe, installed alongside OpenPMD. this one. OpenPMD Pipe is a tool that I think at some point was suggested by René. The idea of OpenPMD Pipe is to redirect data from some data source onto some data sink. And since in OpenPMD we can configure I/O dynamically, this means we can use this tool to, for example, convert from one backend to the other, to compress data that is uncompressed to uncompressed data that is compressed, to read from a stream that is currently running and redirect the stream to disk. For example, you can generally with ADO streaming have as many readers as you like, and they can come and go. So you can, for example, latch onto a running streaming setup and pipe some of that to disk. You can use it for defragmenting very fragmented files. So this is also going to be an effect that we will see, because we just saw we have this decomposition into not very fragmented, but still some blocks in ADOS, since we are going to compress now with one rank that is going to merge everything into one block. So we are going to call OpenPMD Pipe on, please not the entire dataset, but just one of them. So the one that we, something is, why is my terminal not reacting? Someone home? Okay, my terminal is, let's open a new terminal. Might be that the okay, it might be that the file system is currently being slow. So maybe that's also one point that I should make about one thing that I mentioned yesterday. We were able to reach the entire file system performance. This was now done for figuring out if we can do that, but you should still be aware that the file system generally is actually a shared resource, not part of your job allocation. So you theoretically have access to the entire thing, and if you use it, then others will wonder why things like this are happening, because the so generally it's also a good idea to maybe not overburden the file system, except if you do it on purpose. Okay, now we are back in business. But this is also something that we will see again later on when we talk about parallel I/O. So we take this as an in file. Let's just write the out file to the home folder. Since we use the configuration from the configuration file, let's specify it that way. And let's use file-based encoding, or do I use file-based encoding? I didn't specify it, so let's do. And now again, let's load the compression configuration from that file. So by specifying out config and the file name, like this. %t expands to the iteration number, so we write one file per iteration. We only write one single iteration now, so that's fine. And %e is the automatically supplanted extension for the backend that we have chosen. And since we choose that backend here explicitly in the toml config. We don't need to specify it here. We code it, but we don't need to. Richard?
The app is only possible if I execute this from the directory. Is this correct?
It will, yeah. So
if I'm not working in the directory, I can build the full path.
yes, you specify a path relative to the position that you're running at, or an absolute path.
Okay, perfect. Thank you.
Okay, then I'm starting this. Takes some time to load and to write.
You adjusted something in the total file, right?
No. You get an error?
Yeah. The total specification, all the parts in the period.
Did you remember to put an ampersand in front of the path?
Okay, that's why I asked. So I have to put the ampersand on
Yes, because you could also specify the toml configuration inline on the command line. So this little friend here is important. Okay. Now the question might be, why are we using BLOSC? Because from your everyday computer usage, you might know some other compressing tools. In the notebook, I suggest, for example, trying out, which one, bzip. Why are we using compressing tools that are specifically written for HPC usage? I can show you why. So let's, or maybe before that, let's check the file size of the compressed file that we just wrote. It's compressed and useless data. So now let's try this with bzip. And we will be seeing this one for a very long time now.
If you can in between explain the output you're seeing, there's a question in the Zoom chat
Yeah.
About how to read this output.
Yes, so the B, E all charge density and E all energy density are the meshes that are written by this particular Pickon GPU simulation. As I said, Pickon GPU ID provider is something internal that we just store as a mesh for now that is planned to change and go in some more specific internal folder in the future. So we have these 4 meshes. If you remember yesterday, we wrote one mesh and called it heat. And there is one particle species, E, for electrons, and the electrons are defined by the properties such as position and position offset with respect to that mesh. Their weighting is used by Picon GPU to implement macroparticles because we don't simulate at the granularity of a single particle, but rather say there is one particle that actually is, let's say, 1000. Charge and mass are basically physical constants for electrons, and the momentum is the current momentum of the respective particle simulated. So I will now cancel this. Actually, to tell you what is going to happen, the BSIP compressor is not even really taken seriously. It's more as a toy example put into ADIOS. It just doesn't even support data that large, so there will be an error at some point. So yeah, canceling I/O operations sometimes is difficult. So let's do this.
So here it was in the first case that gave the 3.7 results. It was BLOSK.
It was BLOSK, yeah.
And bit shuffle. That was bit shuffle.
Bit shuffle, and the other option that we had in there are further options for the BLOSK compressor. So maybe if you know your way around JSON a bit better compared to why does it show it me that way? Let's do it on the terminal. So this is the JSON configuration. For compressing, you add one operator to ADIOS, to the ADIOS dataset. The operator type, the general operator type is BLOSK, so we are configuring a BLOSK operator, and we can further configure that operator by specifying parameters. So the bit shuffle and the compression level are for BLOSK. Now oh yeah?
So can this be also used when transporting data?
Yes. So the question was if we can use this for transporting data. I guess you mean streaming?
Yeah.
Yes, this will then be used for streaming and send less data over the network. The next thing I'm not done with this particular. René has some plans. With this particular exercise, the next thing would be ParaView. I'm suggesting we have the coffee break now and meet back at 10:20. I think should be enough. Yeah.
Just quickly to say that for the Picon GPU developer, not the user session in the afternoon, I will be using some NVIDIA tooling. So just very briefly, it's not intended to be hands-on, but if you happen to have access to NVIDIA hardware and tooling and would want to follow along, which would be possible, you should make sure to have access to that and get the repository from the slides with the heat equation code onto that. Just not expected, but if you want to follow, yeah.
All right. And also, if you want to follow along with the ParaView session, as I mentioned yesterday, then you should have downloaded already one of these files that we just used. So I'm suggesting to use iteration 1800. Each of them has around 6 GB and have a recent installation of ParaView that, if you want to follow along, you might try to launch now. And as I said, have some free memory, because if ParaView will take the memory that it wants to have, and if you go over memory, especially for the remote audience, that will also mean that you will drop out of the Zoom session because your computer might freeze. So maybe try avoiding that. There is one question.
Would it also make sense to use, instead of the original 1000 BP5, the now compressed BP5? Probably not for ParaView, but for download. You have also using it.
I'm not sure if so the question was if you could download the compressed BP5. Maybe yes, maybe no. I'm not sure if the ParaView distribution compiled with BLOSK. So maybe that works. You can try it out. Also, if you got the file from my USB drive, please unzip. Okay, then we'll meet back at 20. Okay, now let's go on with the cool stuff and visualize the stuff that we just saw in 2D, actually in 3D. Like I said, I'm not myself an expert in ParaView. It was not me who wrote the OpenPMD plugin for ParaView. I just want to show you the kind of images that you can actually make with it. But ParaView is really finally a software that you can do a lot of things with when you're an expert, and I'm not. So maybe as a little introduction now, but generally for ParaView, we could make a whole workshop on that alone, but it would probably not be me who would do that. So if you downloaded the dataset, you will have a folder like this. So like before, the BP output is generally a folder. And the way that you tell ParaView about an OpenPMD dataset is by writing a little text file with the ending .pmd. So, for example, like this. And in there, you write the name relative to the directory where the file is stored of the dataset that you want to open, as you would pass it on to the series constructor.
Sorry. I just saw that you're not joining the audio, but
Yeah.
Okay, sorry.
So let's write that in there.
You press Control Shift Alt H to remove control.
I tried it.
Oh,
It doesn't work. Yes, I know. It doesn't work. I moved it to a point where it doesn't disturb me, but for some reason it doesn't want to. So let's write this like this. Oh wait, let's no. ParaView is still using the old release, which doesn't have this %e syntax. So let's actually be explicit about it. This last command is just for copying the path. And now open this. Into ParaView. And you see here is this, I don't know if you can make this larger, can I? Can maybe try making the whole desktop smaller. No, it doesn't disturb me. Maybe this makes it a bit more visible. You see on the left-hand side, again, the pick on GPU fields and species. In order not to overload our compute capacity, we just select one of the fields and unselect the others. Definitely unselect again the pick on GPU ID provider. And for the species, we are also going to unselect these three and stick with position, offset, and momentum. Now that we have done that, can click apply and make ParaView do its thing. This will maybe take a few seconds.
So how many, do you know how many points? So it will be a 3D block.
It will be 3D, yes.
Yeah. And do you know how many points has the mesh, or approximately?
So the question is how many points the mesh has. You can try figuring it out by running BPLS on the dataset. So there is I think I posted it in the chat something that.
Oh, it depends. 192 times 1,500 something times 200 around.
Okay, yeah. So something has appeared on my computer now. But so the number that René just gave is also only the mesh points, but not the electrons. So you would need to figure that out separately. We don't see much yet, because this is just a default view. So instead, for the meshes, let's up here pick the B mesh where originally the menu says solid color. For this dataset, it's better to plot the colors logarithmically. There is some warning about readjusting the range, which we can happily ignore. And up here, instead of outline, you can, for example, pick surface. It will compute a bit again, and then we see we have the surface visible. Now, this is nice and everything, but it kind of blocks our view. So what instead we are going to do is we will slice the dataset by using a predefined filter by ParaView, which is this one here. So select the meshes up here and then add a filter to the pipeline. It says slice dataset with planes. You see it already suggests one plane. We will stick with that for now and hit apply. Again, there is some warning about readjusting the range. And because this is only one dimension, we will add a further slice along another dimension. Again, clicking slice plane with datasets with planes. And now here, change the normal vector from 1, 0, 0 to 0, 0, 1. Hit apply. Hit apply. And we get this little cut through the dataset, through the mesh, through the B mesh, I think it was, in both directions. For the particles, so as said yesterday, one trick about the simulation is that the laser pulse is strong enough to push the particles out of the observed area. This is a rather small simulation, so really you see in the front space where the simulation has already proceeded into barely any particles left. Still, they're all in some weird white color. Let's instead decide to visualize the momentum and again use the log scale. Again, ignore the warning. And you see here now that the particles are colored by where they are being affected by the pulse. And the nice thing about that really is, again, by standardizing data, this plugin was written not for Pick on GPU data, but for WarpX data originally. Was developed mainly by applying it on WarpX data. But since both Pick on GPU and WarpX use the same standard, we were able to reuse that work and now have a visualization basically for free. That implicitly understands our data and we don't need to fiddle around with manually loading things into ParaView and learning how to do that. And we can also use the custom transformations that ParaView has. For example, just showing one thing, integrate streamlines into a vector field. Let's again select the meshes to do that. In order to visualize trajectories that occur within a field along a line, this by default selects this diagonal line. Let's not stick with doing this diagonally, so instead pick this point divided by 2. No. to set things generally into the center of the x-axis here and of the z-axis here. So the line is now aligned along the laser pulse. Can hit apply. This will again calculate for a minute. Move that bit. And this is maybe a bit of a cooler representation of the data compared to the thing that we, to the simple one based on Matplotlib that we saw before the pause. Like I said, this is more intended for showing what you can do and giving a little hint into the directions of what can be done with this kind of data, but not intended as a comprehensive introduction into ParaView, which I simply don't have the time and also not the knowledge for, so there are others. I think someone posted something in the chat right now. There was also recently at LBNL by Axel Hübel a course, an introduction on ParaView. I don't know if he uploaded the video yet. I need to figure that out. Yeah. So, ParaView, cool thing. Even cooler if you know it. Better than I do. So, I will maybe... The question is, does it have plugins for Nexus data standards or any going work to that? I need to redirect that question honestly to the audience. If someone knows about it, I'm not aware of any work going in the direction of supporting Nexus in ParaView. René is looking startled.
I'm not exactly in the group who are working with that. There are discussions between within our group with the Nexus developer or standardization committee, and we are trying to bring in that Nexus data can be written over OpenPMD. So that you can instead, so that the Nexus format is not HTML5 anymore, that it becomes something like OpenPMD or is using OpenPMD, and you can extend the standard of OpenPMD to support everything Nexus is currently supporting. But for now, OpenPMD is not supporting Nexus. So Adios.
I think the question was more towards Nexus support within inside ParaView.
Oh, okay. That's I don't know. I think so, because
might
it's a well-known format.
It might be, but
yeah.
Either someone in the chat knows, or you will have to figure it out. I don't know about it.
Yeah.
All right. Yes, readers can be added to ParaView by users, so you can definitely load data manually. That's basically what a plugin, if you have written it, does. Just if you have a plugin, it works automatically. But if you don't have a plugin, you can still interact with ParaView manually. Also, the plugins for ParaView are generally written in Python, so you can basically use the same API. Or if you find out that a plugin does things that you need, but not everything that you need, you can also, it's what I have done already, look into your ParaView download that you have on disk, edit the files there, and for example, in the days where the OpenPMD plugin was very young and supported basically only WAP-X, I still needed to fix some bugs directly in the files there. By now it has matured a bit, but still things are in doubt configurable if you actually need to delve into things. All right, that is it for what I wanted to present here. Let me quickly have a look at the chat. Definitely thank you to everyone who Especially thank you to Martin for suggesting further reading and further viewing. All right, I would then close this bit again. Stop share, stop share, stop share. Okay.